All right, let's dive in and unlock one of the most powerful tools in multivariable calculus, the double integral. This is where we take a huge leap from just calculating the area of flat shapes to measuring the volume of entire mountains, all using one single elegant idea.
So here's our game plan. First, we're going to build up that core intuition, making the jump from area to volume. Then, we'll pop the hood and look at the calculation engine itself. After that, we'll get our hands dirty tackling tricky, non-rectangular shapes, unleash a serious superpower called polar coordinates, and finally, we'll see why all of this really matters.
Okay, first things first. Let's build that core idea. What in the world is a double integral, and what does it actually look like?
So you remember from single variable calculus how we found the area under a curve, right? We'd add up all those tiny little rectangles. But what if you need the volume underneath a whole surface, something complex, like a wavy sheet or the side of a hill? Well, that's the exact question that pushes us out of the 2D world and into the third dimension.
And the answer, of course, is the double integral. Honestly, the best way to think about it is just as a level up from what you already know. Instead of adding up values along a single line, we're now adding up them over an entire two-dimensional region on the floor.
And this is the core strategy right here. We take a big, complicated 3D shape and we chop it up into an infinite number of tiny little columns or prisms. We can easily find the volume of each one of those, and then integration does its magic and sums them all up for us. It's a classic calculus move, isn't it? Break a huge problem into infinitely many small, easy ones.
Okay, so the concept makes sense, but how do we actually do it? How do we turn this cool idea into a hard number? Let's go ahead and fire up the calculation engine. Now, this is a super important distinction, and honestly, it's something that trips a lot of us up at first. The double integral is the big idea. It's the what. It's the total volume we're trying to find. The iterated integral, on the other hand, is the how. It's our practical, step-by-step tool, just a pair of regular old integrals nested together that lets us actually find that volume.
And the bridge connecting the what and the how is this incredibly powerful idea called Fubini's theorem. What it basically guarantees is that for most functions you'll encounter over a simple rectangle, it doesn't matter which order you integrate in. You can do x then y or y then x and you'll get the exact same answer. And that gives us a ton of flexibility to tackle the problem from whatever angle is easiest.
And the process itself, well, it's actually pretty methodical. You just work from the inside out. You solve that inner integral first. And here's the trick. You pretend the other variable is just a constant, like the number 5 or something. Once you solve it, you're left with a new, simpler function. Then you just pop that result into the outer integral and solve it like normal. See? You've cleverly turned one hard 2D problem into two much easier 1D problems.
Right, so rectangles are great and all, but let's be real. The world is not made of perfect rectangles. The real power of this tool comes when you know how to handle more complex, curvy shapes. So let's tackle that right now.
So our first strategy is to define our region as what we call a type I region. All this means is that we're thinking about it in terms of vertical slices. Our region is sort of sandwiched between two functions of x, while x itself just moves between two simple constant numbers.
This visualizes it perfectly. When we say vertical slices, picture a line moving from left to right. For any x value it hits between a and b, it enters our region at that bottom curve, g1, and it leaves our region at the top curve, g2. And those functions, they become the limits for our inner integral. And here's a real example. If we wanted to find the volume over this shape, our outer integral for x would have nice constant limits, just from -1 to 1. But that inner integral for y, its limits would be functions, from the lower parabola, 2x squared, up to the top parabola, 1 plus x squared. But we can also slice it the other way. We can use horizontal slices instead, and we call that a type 2 region. Now, choosing between slicing vertically or horizontally isn't just a style choice, it's a massive strategic decision. Sometimes one way will give you a really simple integral, while the other way leads you down a path of mathematical pain.
All right, get ready for a technique that honestly feels like a cheat code in calculus. This is where things get really fun. We need to talk about polar coordinates. I mean, just look at this integral. If you try to describe a circular shape using plain old x and y, you get these awful, messy limits with square roots all over the place. Trying to solve this thing directly is, well, it's a nightmare. It's possible, but not fun.
And what this all boils down to is that we're just using the wrong tool for the job. It's like trying to build a perfect circle out of a bunch of tiny squares. It's clunky, it's inefficient, and it just creates a ton of unnecessary work for anything that's naturally round.
So, what's the solution? We switch to polar coordinates, using a radius r and an angle theta. But here is the absolute secret sauce, the magic ingredient you cannot forget. The area element, dA, becomes r dr d theta. That extra r is absolutely critical. It's a correction factor, because the farther you get from the center, the bigger the little area slices get. Forgetting that r is probably the #1 mistake people make.
And just look at the payoff. That same horrible, complicated integral suddenly becomes, well, it's beautiful. The limits are now simple constants, the function inside cleans up nicely, and the whole thing becomes incredibly easy to solve. That right there is the power of choosing the right coordinate system.
Okay, so we have the theory. We've got some cool tricks. But let's bring it back to reality. Why does any of this actually matter?
Well, it turns out double integrals are everywhere. They're not just for finding some weird abstract volume. If you just integrate the function f of xy equals 1, you actually get the area of your 2D shape. In physics, they're essential for things like calculating the mass of a metal plate where the density isn't constant, or for pinpointing its center of mass. And in statistics, they're the key to figuring out probabilities.
But, like with any powerful tool, there are some really common traps you can fall into. And some fascinating research actually highlights one of the biggest pitfalls students face, especially when they're trying to calculate plain old area.
So here it is, the pro tip you have to remember. The boundary functions, the g of x or h of y, their only job is to define the shape of the region on the floor. The function inside the integral, the f of xy, that's the height of the ceiling. And when you're just finding area, the ceiling is just flat, at a height of 1. Don't mix up the shape with the height.
At the end of the day, this tool fundamentally upgrades our ability to analyze the world around us. We can now move from simple lines to complex surfaces, opening the door to measuring all sorts of things that were totally impossible to calculate before. So the only real question left is, what are you going to measure first?